Welcome back, everybody. Let's talk about energy changes in chemical reactions. During a chemical process, your energy can either be absorbed or released. So we've already talked about a couple different kinds of energy earlier this year. We talked about thermal energy, which is energy of the motion of the particles, and we saw that as temperature. We measured that as temperature when we talked about that because our system was staying the same. So as the particles move faster, there would be more thermal energy. We talked about phase energy, which was the energy due to the spacing of those particles. And we talked about that in terms of the state of matter, solid, liquid, gas. What we're going to focus on here today are changes in chemical energy. Chemical energy is just one type of potential energy, and it's the energy that's stored in the chemical bonds of our different compounds and elements. And often what we're going to be looking at is how that chemical energy changes as we go from reactants to products. We are rarely going to talk about just the absolute, how much energy is stored in my molecule. Usually we're looking at how do things change during that chemical reaction. Now, chemists tend to talk about a term called enthalpy, and that's focusing on the change in enthalpy in a reaction. Enthalpy in many ways is a measurement of this chemical energy. Specifically, if you're under constant pressure, the change in enthalpy will be equal to the heat that's transferred during that process. And as such, it really takes into account a lot of these different types of energy associated with it. Let's take a look at just a minute at how I wrote this expression. So the symbol for enthalpy is H, and so the change in enthalpy is delta H. Don't ask me why enthalpy is H, it's just a historical piece. And so the change in enthalpy during a chemical reaction, so I have the subscript Rxn after delta H to indicate that that is my change in the enthalpy, so all these different types of energy, as the reaction is occurring. And that's equal to Q. Remember Q from earlier this year? Q was heat. So that's equal to the heat that's being transferred. And this is true under constant pressure conditions, which is an awful lot of what chemists do. And so we're going to work with enthalpy in this context. So for our conversations in class, enthalpy is equal to the heat that's being transferred during a chemical reaction and is a result in the changes in energy of your reactants as you move towards your products. We are going to pull back our LOL diagrams from earlier this year and use these as our first level of representing how our energy is changing during a chemical reaction. So what we're going to introduce, we had ETH and EPH earlier this year. We're going to work with ECH for chemical energy. And I am only going to focus on the changes in chemical energy. I'm not going to try to track both chemical energy and phase energy and thermal energy all at once. We're just going to focus on our changes in chemical energy for this conversation. So let's take a look at an example how we can use this. When you have a double replacement reaction between barium nitrate and sodium sulfate, you are going to produce barium sulfate and sodium nitrate. And in that process, the system gives off energy, which makes the surroundings warmer. And so you see my chemical equation written down below. When we're talking about heat processes, we're going to make sure we include our state symbols because energy is associated with that state. And off to the right, you'll see I say delta H of reaction is negative 67 kilojoules per mole. So the fact that it's negative means that that energy is being given off. If we try to visualize this with a LOL diagram, let's say we're starting with 3 blocks of energy. Remember, our starting point is arbitrary. And the reaction is my system. And I'm not going to try to fit the whole equation into that little circle. So I'm just going to write Rxn, since that's the kind of universal abbreviation for reaction. Now, delta H here is negative, which means that energy is going out of the system and into the surroundings. So if I lose 1 block of energy, when I'm done, I'll have 2 blocks of energy. This is an exothermic process. Hopefully you remember this from earlier this year. Energy is being lost from the system, and so it's exothermic. It's going into the surroundings, so the surroundings will get warmer because it's gained that energy. But from the reaction point of view, this is an exothermic process. Let's take a look at one more example with this LOL chart. Let's say I've got water. When I break water into its component elements, into hydrogen and oxygen gas, I have to add energy to the system in order to do this. You actually did this in class earlier this year. We used a battery as the source of that energy. But I have to put in energy. And it turns out for 2 moles of water forming 2 moles of hydrogen gas and 1 mole of oxygen gas, I have to add 572 kilojoules of energy for every time the reaction occurs. That's what the per mole RxN indicates. It's each time the reaction happens as it's written. How much energy do we have to add in this case? If we start with, again, 2 blocks of energy, starting point is fairly arbitrary. I've got my reaction. Delta H is positive. I have to put energy in. So I'm going to put energy into my system. So when I'm done, oh goodness, I kind of went overboard with my little blocks. I'm going to have 5 blocks of energy to be consistent with the picture that I've drawn. This is an endothermic process. I am putting energy into my system. I do want to point out, as you look at this, it's really easy to talk about when you've got this diagram in front of you, how the potential energy of the reactants and products, the chemical energy of the reactants and products, are relative to one another. So in this case, my reactants have less chemical energy and my products have more chemical energy. And so I know I've put energy into the bonds associated with those molecules. If we talk about what you, the observer, would experience if you were watching an endothermic or an exothermic reaction, we can talk about how the energy would change as well as what you would actually see or sense or measure if you were there. So in an exothermic reaction, we know that energy is transferred from the system to the surroundings. And so this is your system releasing energy. Well, if your system releases energy, you, the surroundings, or the observer, are going to end up gaining that energy. And so if you gain that energy, perhaps you will have a change in temperature, as in the surroundings, whether that's the beaker of water that the reaction's occurring in, the air around the reaction, or your hand that's touching the reaction, you might experience an increase in temperature. Things might get warmer or just downright hot. Another way to kind of harness that energy is we can generate electricity from that exothermic reaction, and we can harness that energy. On the other hand, if we have an endothermic reaction, in an endothermic reaction, energy is being transferred from the surroundings into the system. And I want to emphasize here, when we're talking about the system, we're talking about the particles involved in the chemical reaction. That's what our system is. Well, if you're having to put energy into those particles, into that chemical reaction, that means the surroundings, you, the observer, or whatever is nearby, is going to decrease in energy because you're giving the energy to the system. And so what you would experience here would be that if you have a beaker full of water and the reaction is going to happen within that beaker of water, the reaction takes the heat in, the water loses it. The water actually gets colder, or the air would get colder surrounding this endothermic reaction. Or perhaps you need to provide energy in the form of electricity. So you're going to provide or input electricity. The reason I'm pointing this out specifically is because this idea of the beaker gets cold, is my reaction endothermic or exothermic, is one that often confuses people. If the beaker of water surrounding the chemicals gets cold, that means that it has lost energy which has gone into the reaction. So that is an endothermic process. If your beaker of water gets hot or the surroundings get hot, that means the reaction is giving off heat. So you have to remember to think about flipping it from what you, the observer, experience to what the chemical reaction is doing.